How's everybody doing out there? Well, welcome to day 8 of Corona Online School. And today we're continuing our study of probability. So today we're actually moving on to what's called the multiplication rule or and type problems and conditional probability. So up to this point, we've calculated like individual probabilities, like the probability that A occurred, the probability of B occurred. Then we looked at the probability that A or B occurred, which if you think about it meant that they couldn't occur at the exact same time. So now what we want to talk about is the probability that A and B both occur, which means that they actually would be able to occur at the exact same time. So what we're going to do is we're going to look at two different kind of questions here real quick, just to kind of set up the two different types of scenarios we're going to have. So if we look at example 1, flipping a coin twice, if we flip a coin, the sample space is such and such. So in this case, we've got our sample space is going to be, so we could flip heads and heads, or we could flip heads and tails. We could flip tails and heads, or we could flip tails and tails. So in this case, we've got 4 things that are in our sample space. And so the first question is, what's the probability that the first flip results in a heads? So in this case, if we look at our chart, so we don't really care about what the second coin does at the moment. We only care about what the first coin. So if we look, we've got 2 possible choices for ways to flip a head first. So in this case, that would give us 2 out of 4, or if we reduce it down, a 1/2 chance of flipping heads first. So the second one is, what's the probability that the second flip results in a tail? So again, this is going to be the same kind of idea. We want to look and see just the second one and whether it's a tail or not. So in this case, so that would be a tail, and that would be a tail in the second position. So lo and behold, there's 2 of those out of 4. So again, that gives us a 50% chance that we flip a tail as the second choice. So now what we want to do is kind of combine this together and look at what's the probability that we flip a head and the second flip is a tail. So in this case, it has to be both. So we have to have a head in the first position and a tail in the second position. And so if we look, there's only one of those actually in our chart up there. So in this case, we'd have a 1 in 4 chance of actually flipping a heads first and then a tail. All right, so if we kind of look, that the probability of both these things happen together was 1/4. But if we also kind of notice the probability of these guys individually was 1/2 for the heads times 1/2 for the tails. And so if we multiply those together, that also gives us 1/4. So at this point, we may be asking the question, so does this happen all the time? So if I've got, the probability of A and the probability of B, do I just multiply them together? And so the answer is sometimes. So not all the time. And so let's look at the next example so we can see why this doesn't actually work in this case. But it is kind of on the right idea. All right. So for example 2, what we're doing is drawing 2 cards without replacement. So this is important to notice here. So what this means is when we're not placing it back in the deck, that means we're just kind of leaving it on the table. So what's going to happen is it's going to change the outcome of the deck of cards and stuff. So in this case, again, we're using a standard deck just like we had pictures of in other situations. So if I ask, what's the probability of drawing an ace the first time? So if we look at our little tree diagram that we've got down here, there's 4 aces and there's 52 cards. So the probability of me drawing an ace on the first card would be 4 out of 52. And then if I kind of went down the tree the other way, not that it technically matters for this problem because we want to know what's the probability of drawing 2 aces, but just in case. So not an ace would be all the other cards. So in this case, if we do 52 minus 4, that would give us 48 out of 52 in this case. So now if we kind of follow this tree diagram up, so this is our first card. This whole section here is our first card. And this will be our second card. And again, without replacement. So the probability of getting an ace after I already got an ace the first time. So remember, like maybe the ace of hearts is sitting here laying on the table. So there's one less ace that's in the deck. So that means there's only 3 possible aces that are left. But also, we've reduced the amount of cards in the deck because that ace of hearts was still one of the cards. So that means there's only 51 possible aces that are left in the deck in this case. And so if we did the branch the opposite way and said, well, what happens if we didn't get an ace this time? What would be the probability? So in this case, so we got an ace the first time. So again, that means we're down to 51 cards. But again, even though it was an ace the first time, so there's still 47 cards left. Because in this case, we got rid of one of the cards, so we still have that many that are left over. So they're not an ace. Oh, let's see, is that right? So we used an ace. So we're down to 51. So there'd be 3 left. 48. Sorry, 48 out of 51. I misadded. All right. So same thing if we kind of continued on this 48 over 52. So in this case, oops, sorry. So in this case, if we got an ace this time, so in this case, if we got an ace, so the probability of getting an ace this time was there was 4. Ace is still in the deck because we didn't get an ace the first time, but there were 51 cards left over because we already used one in that case. And then finally, not an ace this time would mean that we didn't get an ace the first time, so we didn't get an ace this next time around. So in this case, we'd get 47 out of 51. So we'd end up with 1 card less, but again, 1 card from the not ace pile left also. And so ultimately, all this other part doesn't really matter. The only part that we want to focus on is kind of this top part of the tree because that's where we're getting 2 aces in a row. So the idea is to get the probability of an ace first and then an ace second time around, we get 4 over 52 times 3 over 51. So let me put that down here. And again, the reason we did this is because it's without replacement. So once we use the card, it disappears and we have to eliminate it from the group that we were trying to get the probability of, but also from the total at the bottom. And then if you were to multiply these together, you would just multiply them straight across the top. And then, I forgot my calculator again, but just 52 times 51 on the bottom. So to get the probability of an ace 2 times in a row without replacement would be 12 over 52 times 51. So the second one is what we call conditional probability or dependence. So these two are going to fall into 2 different categories. So example 1 is what's called an independent event, which we'll see in a second means that the probability of the second thing happening doesn't have an effect on the first thing happening. So they're independent events. The probabilities aren't going to change or anything like that. And the second example is what's called a dependent event. And again, this is dependent because we kind of threw that 1 card away, and because of that, the second probability ended up being different. So it's dependent, or sometimes it's called conditional probability. Usually I'll just use the word independent or dependent for these guys. All right, so let's kind of look real quick. So this is what I just mentioned with independent events. So two events are independent if the outcome of one has no effect on the probability of the other occurring. And so the first example was independent because we were flipping the coin, and just because I flip our heads on the first time, I'm not going to be less likely to flip a heads the next time. The probability is 50-50 either way. And so saying the two different events are independent is different than mutually exclusive. So keep that in mind. So mutually exclusive is an addition thing. So this has to do with addition and OR problems. And independence has to do with multiplication and problems. So again, two events are independent. They have no effect on each other's likelihood of occurring. And another thing that happens with independent events is they can happen at the exact same time. So like having two heads with a coin is something that can possibly happen. But two events that are mutually exclusive, they can't ever occur together. So since it's an OR problem, you're going to get one or the other. You're not going to get both in either one of these situations. So that's another thing that makes it different from an independent problem. So again, independent is and multiplication, mutually exclusive is or addition. All right, so let's look at example 3 real quick. And what we wanted to do is determine whether these are independent or dependent events. All right, so a fair coin is tossed 2 times. The two events are A equals the first toss is heads, B equals the second toss is heads. So again, since these are coins, I'm not less likely to, flip heads. It's not like I took the head off the coin or something like that. So in this case, this would be an independent event. All right, so what about something like two events, and A being it will rain tomorrow in Frederick, and B it will rain tomorrow in Thurmont. So this doesn't seem like it's probability related, but Frederick and Thurmont are relatively close together. So more than likely, if it's raining in Thurmont, it's probably raining in Frederick and vice versa. I mean, sometimes it can happen that it wouldn't be, but the likelihood that it's raining in one place and not the other is not very good. So in this case, this would be a dependent event. So because it's raining in Frederick, more than likely it'll be raining in Thurmont and vice versa in that case. All right, so as part C, I draw a red card from a deck, then draw a second card without replacing the first. So again, this is the key word, without replacing. So in this case, I grabbed the first red card, ripped it up, threw it away. Then I drew the second red card. So in that case, again, since it's without replacement, this would be dependent because the probability the second time around is going to change because I ripped that card up and threw it away. All right, so D, you draw a face card from the deck, then you replace it and reshuffle it. So again, that's the key word here. So we've actually put the card back into the deck before drawing a second card. So in this case, so maybe I drew the King of Hearts the first time, but now I stuck it back in the deck, so it's possible I'll actually draw the King of Hearts the next time. So since it's there, this is an independent event in this case. All right, everybody okay with that? All right, perfect. All right, so here's just a little bit of a summary of the rule. If the probability is an independent event, and so it's exactly like we demonstrated above, you just multiplied the two probabilities together, or in the case you had multiple events, like K events, then again you would just kind of multiply each of these guys together. So this looks very similar to the addition rule, it's just, we're using multiplication and. All right, so the next couple here, practice 1 and practice 2, is using independent events. So I'll leave these guys for you to practice. And then I'm going to move on to the conditional probability or dependent events. And so at this point, pause the video, do those couple practice, and then come back and catch up with what we're doing here. All right, so multiplication rule for dependent events or conditional probability is the probability that B happens on the condition that A already happened. So again, think about it like a deck of cards where we just ripped the card up and threw it away, or if we had a bag of M&Ms, we were eating each bag after we counted them, or eating each M&M after we counted them. So the notation for this is the probability of A with a line, or probability of B with a line, then A. So that means the probability of B occurring, assuming A has already occurred. So this means the probability that B occurs, assuming A already occurred. So again, just like kind of our first example that we had, the probability on the ace of the first draw would be the 4 out of 52 because all of the aces are there. But then an ace on the second draw, assuming that we got an ace on the first draw, means that we get 3 on the top because there's only 3 aces left, 51 on the bottom because there's only 51 total cards left in the deck. And so in that case, we end up with 1 over 221. And so if we look, the multiplication formula for dependent events is pretty much similar, except the only difference is instead of just the straight probability of A, it's going to be this new calculated probability of B based on the fact that A has already occurred. And then the little footnote below, just like for mutually exclusive, in the case that A and B are independent, like then the probability of B, assuming A occurs, would just be the probability of B, and we get the original rule that we had before. All right, so with that in mind, I was going to have you guys try a couple of these ones that are, without replacements, so the dependent probability ones. So try practice 3, practice 4, practice 5. And then the last thing I wanted to do, so again, pause the video at this point, go practice those guys. And then I wanted to talk a little bit about doing probabilities using a contingency table. And so I think this is the same contingency table we had in the last example. So we've got FCC students with their major kind of down the left, whether they were right or left-handed across the top. And so we want to know what's the probability that a randomly chosen student is an education major, given that the student is left-handed. So in this case, we're looking for, if we were to write it out, the probability of an ed major given, so in this case, I'm going to use the line for given, that the student is left-handed. So when we're looking at this, like all we have to do is kind of focus on like the last part in this case. So in this case, we want to know, it's because we're looking for the education major and we're looking for whether they're left-handed or not. So we know that they're left-handed, so that means we only have to kind of look down this list. So we know the student's left-handed. So now we're just kind of focusing on the education part. So in this case, what's the probability that a randomly chosen student is an education major given that the student is left-handed? So in that case, we get that there are 13 left-handed education majors out of how many total? So again, the last numbers kind of give us the denominator in this case. So we're looking for the 25 because those are the only students that we're actually drawing from. So the bottom number in these conditional probabilities is always going to come from the given, like given that this person was left-handed or given this person was right-handed or whatever. So that's where we're going to get that bottom number from. The top number is going to come from where those two rows and columns actually intersect each other. All right, so let's look at B. So what's the probability that a randomly chosen student is right-handed? Whoops, not thinking right-handed, and supposed to be writing probability. So right-handed, given that the student is a math major. So again, in this case, let me clear out all these marks. So for this one, so now we want them to be a math major. So that means right away we can write down our bottom number is going to be 59. And what kind of math major do we want? We want right-handed math majors. So again, we're looking for where does the right-handed and math majors combine, and that becomes our top number. And so we end up with 47 out of 59 in that case. And again, you can leave it as a fraction, turn it into a decimal, whatever. All right, is that okay with contingency tables? Perfect. All right, so I do have some in here in the back. So this is a nice little exercise for you. So it kind of combines 3, 2, and 3, 3 together. So you're trying to go through and decide, is this an or problem or is it an and problem? And it should be pretty apparent, like in the question, but if you do have questions about it or anything like that, give me a holler. So work on practice 6, and that will finish us up for 3.3. So if you want to pause this, finish practice 6, we'll come back and look at 3.4. Good luck.